OK. So homology is what we're studying. And there's one thing which I didn't mention yesterday, which is that the nth homology of a space, that really means the nth homology of a space with coefficients in Z. And you may vary the coefficients. So you pick whichever abelian group you like. It could be Z, or it could be Z mod 2, or it could be the rational numbers. And there's a version of homology that takes coefficients in that abelian group. If I just write it like that, then it could either mean I mean this, or it could mean I'm going to say something that works for any coefficients, and I'm just lazy and not writing down which coefficients work. Anyways. Here's some terminology that I'm going to introduce in a moment. There's the notion of n-dimensional chains, n-chains. It's always for some topological space X. There's a notion of n cycles. There's a notion of n boundaries. And then there is elements of this group which are n-dimensional homology classes. And there are some standard names for these. So n chains is denoted Cn, n cycles is denoted Zn. So Cn of x, Zn of x, because the word cycle in German starts with the letter Z, and n boundaries. So before defining them formally, so these are all abelian groups, and all of these depend implicitly on a choice of coefficients that is not denoted right now. So before defining them formally, I will tell you how they're related. So these are I guess this one is also an abelian group. They are related in the following way. N chains, that's the most general thing. So the n chains on X contains as a subset, indeed as a subgroup, the n cycles. And the n boundaries are an even smaller subgroup. And then we also have that Hn of x is the quotient of the cycles by the boundaries. So let me take an example and show you what a typical element of these various groups looks like. So I'm going to take my space X to be the same example that I had before. Looking for this thing up. So a typical element of Cn of x, here I'm taking n equals 1 just for the purpose of drawing things that are easier to draw. This is a typical example. It's something that, at the end of the day, does not represent a homology class. Like homology classes need to be closed loops. And that's not a closed loop, they're just like a little path. But these are going to be useful in defining Zn, the set of cycles, as certain chains that happen to be closed. If I want to give you an example of something which is allowed to represent a homology class, well, here's an example. And finally, the boundaries are things that exist but represent the element 0 in homology. You want to mod them out. So here's an example of a boundary. Indeed, that boundary, you can continuously deform it, say by pushing it to the right, all the way until it falls away. And through this deformation process, it will become two things, and then become again one thing, and then become 0 things, and then disappear. So that is an element that represents 0 in H1 of this space. Why are these things called chains? Because these are going to be, once we formally define them, a slightly better way of drawing them is going to be maybe something like that. It's going to be a path, and then another path, and another path. So these are chains of paths, and that's why the name chain. Cycle, that's intuitive. It just means that it closes on itself. And the boundary, why is that called a boundary? Well, that's called a boundary because this thing here is the boundary of this guy in red. So you have this thing, which is a two-dimensional thing in red. What is its boundary? It's the thing in green. And so hence the name boundary for those. OK, so this is a bit of intuition of these things that I'm about to define. Let's define them. We'll start by this. The n chains on some topological space X with coefficients in some abelian group, which I call R. The reason I call it R is that in most cases, the type of things that you want to use are going to be rings. That's actually not needed. You can use any abelian group. But in practice, what you end up using is a ring. And so I use the letter R. So this is the free R module on the set of all continuous maps from an n-dimensional simplex to X. OK, let's unpack what these things mean. What does it mean to take the free R module on a set? That's something that you might have seen. So the free R module is the set of all maps from S to R. S is a set, R is a ring, or an abelian group. Sorry, I'm using, here I've secretly started using terminology that is only allowed when R is a ring. And that's because I very much intend to take R to be a ring. So I'm not allowed to say that. Really, I have to say the infinite direct sum indexed over the elements of that set of copies of R. So it's the infinite direct sum indexed over elements which are continuous map from delta n to X. And what is it that I'm summing? I'm summing R. And this infinite direct sum can also be written as the set of all maps from S to R that send all but finitely many of these elements of S to the element 0 in the abelian group R. OK. So this is sort of in parentheses because you're not allowed to always say it. Anyways, this is what it is. So how should I think of it? The way to think about it, you think of it as being it's a finite linear combination of these maps where the coefficients are taken in R. So really, when I drew this thing here, I drew 3 little paths. Implicitly, what I mean is the following. Implicitly, I mean R is a ring, so there's an element that's called 1, and then I put 1 times this plus 1 times that plus 1 times that. If R was not a ring and was just an abelian group, then this wouldn't have a sort of automatic meaning unless I say what the coefficient is. So
does R have to be commutative?
Yes, R is a commutative. It's an abelian group, yes. Abelian group. So this is an abelian group, and often a ring, even though that is not really necessary. So if it's a ring, you may use either this or that. If it's an abelian group, you're not allowed to use this, you use that. But that's what it means. And this means continuous maps from delta n to x. I didn't tell you what delta n is. Delta n is what is known as the standard n simplex. OK? So here's the standard n simplex. The standard n simplex. It is the convex hull of the standard n+1 basis vectors in Rn+1. So what is it in practice? Let's draw this for delta naught, delta 1, delta 2, and delta 3. So delta naught, I'm supposed to take Rn+1, which is a line, and then I'm supposed to take one element in that line. It's this element here. That's not the origin, that's the element 1. And the convex hull of this one point is a single point. Great. Here I have R2, and it has an axis here, an axis there. And the two elements that I'm taking the convex hull of are this one and that one. And I draw a line. So the thing in red is the standard 1 simplex. That's just a segment. Here in 3 space, I have 3 axes, and I have 3 points, and I take the convex hull, which is a triangle. Delta 3 is a thing which is intrinsically 3-dimensional, but the way it's defined, it's embedded in R4. Well, R4 isn't something I'm going to draw here, but delta 3 is something I can draw. Why do we pick that specific definition? The answer is it doesn't matter. I have to somehow pick a definition, and I may as well pick this one. If you have some other standard way of selecting n+1 points somewhere that you can take the convex hull, you're allowed to do that. But let's say that's the one we work with. So a simplex is a generalization of a triangle in higher dimensions. And why are simplices good? Simplices, which is the plural of simplex, simplices are good because they are versatile, and I can build any shape I want out of simplices. Any surface can be triangulated. Any high-dimensional manifold can be made out of simplices. If I had chosen some other standard shape to work with, like cubes, well, you can't quite make everything you want out of cubes as easily as you can with triangles and their higher dimensional generalizations. So OK. What are n cycles and what are n boundaries? To define those, it's important to think about an operator called the boundary operator, which goes from chains of dimension n+1 with coefficients in R, and R is somehow going to be suppressed here from this discussion, to chains of dimension n. So implicitly, there's an index n here. Let's put it here. Let's say delta n. So this is so that's a linear map. Sorry, it's a homomorphism of abelian groups, which intuitively takes the boundary. So here in red, I have drawn actually an element of C2. This thing, well, right now I sort of just shaded the whole thing, but imagine that this red part has been triangulated, and for each one of these triangles I have picked an actual map from this standard 2-simplex into my space X, and then I form the sum of all these things, of all these elements. So then that's an element of C2, and this element in green is what I want the image to be under that map. So I'll tell you in a moment what this boundary operator is, but assuming you have that, then the boundaries is defined as the image of this guy. Sorry, I think I'm going to change my convention and have it go from n to n minus 1. So then it's the image of n plus 1. And the n cycles is defined as the kernel of this thing. So what makes the picture in blue there, the leftmost, what makes it be not a cycle is the fact that it has a non-trivial boundary. What is the boundary of that thing? It's this and that. That's a boundary. So it's not in the kernel of this boundary operator. The thing in red doesn't have a boundary. So it is in the kernel. And over there, that's something which is in the green thing is in the image of this boundary operator. What I told you here when I said that these two red points is the boundary of this thing in blue is a small lie. The reason it's a lie is that actually the boundary is this times 1 plus this times minus 1. So it's not this plus that, it's this minus that. And why is that relevant? Because I want these two things to cancel out when I go to this particular situation. I have a path. It's just a chain. It's not a cycle. If the beginning point and end point of that path agree, then I want that to become a cycle. So I want this and that to cancel. They better have opposite signs, otherwise they won't cancel. If you take R to be the ring Z mod 2, then you don't need to worry about signs, and the whole story becomes a little bit simpler. But we want it to work in general, so we have to worry about the signs. So, OK. The boundary operator allows us to define this and that. What is the boundary operator? I want to define an operator on this abelian group, which is this direct sum of copies of R. It's enough to do it on the, I want to call them basis vectors, on somehow, you don't need to treat a general linear combination when you want to define a map out of something. It's enough to define it on simple things. So I'm going to take a simple element here and tell you what its boundary is, and then that's going to tell us what to do when I have a general linear combination of these guys. So typical element here is written in the following form. Sum over some indexing set, which is a finite set, I equals 1 up to n. Well, it's a finite sum. And then I have a coefficient, r sub I, times sigma sub I, where r sub I is an element of R, and sigma sub I is a continuous map from the n simplex to x. So you think of that as being a coefficient, and you think of that as being, essentially this thing is just a label that tells you in which copy of R you're going to put little ri. So we will define this boundary operator in such a way that if I want to feed it to a linear combination of these sigma i's, it's enough to know what happens to sigma I, and then you put this as a coefficient. So it's really enough to tell you, given this, we define its boundary which is going to be an element of the n-1 chains on X with coefficients in Z. We define it as follows. There's something a little bit tricky about the way I wrote things. Here I have something where the coefficients live in R. My R is an abelian group, nothing more than that. And I'm proposing to use this formula. This is something that has coefficients in Z. So here I have some numbers that are floating. This is itself a sum of things where there's a coefficient, and the coefficient is something in Z. So I have something in Z and something in my group. So I need to combine them to form a new element of my group. Implicitly, I'm using the fact that an element of an abelian group times an element of Z together makes sense and produce a new element of my group. So this is not something to worry too much about. This is just a thing. The notation is made so that it sort of flows smoothly. But let's actually define things, because I'm sort of circling around the pot without telling you what this is. This thing is. So the boundary of sigma. So sigma is a map from delta n to x. The boundary of sigma is a sum of n plus 1 terms, index from 0 to n. And what I put here is sigma restricted to OK, this is a funny notation, which is going to be quite convenient later on. Let me tell you what it means. So these numbers, 0, 1, up to n, are the numbers that I use to label the vertices of my n simplex. This one has only one vertex labeled 0. This one has two vertices labeled 0 and 1. This has three vertices labeled 0, 1, 2. This one has four vertices, 0, 1, 2, 3, and so on. And when I say take all the vertices except I, and I put these square brackets, what I mean implicitly is take the set of all these vertices and take the convex hull of those. So if I took a map from delta 2 into some space and I say restrict to just 0, 2, really what I mean is look at this segment and see where that segment maps. Actually, what I mean is look at that segment, identify it with this segment in the only reasonable way, which is the way that preserves the order of these vertices, and then do that. So really what I have is I have a map from delta 1 to delta 2 that includes this segment in this segment, and then I compose that map with the map sigma. So let's spell that out explicitly. Where sigma restricted to this thing, that's a new map, which is now a map from the n-1 simplex to x. Okay, the n-1 simplex is a subspace of Rn. So I'm going to give it x0, xn. I have n coordinates. And that's going to be defined to be, oh, that's wrong, sorry. I forgot something very important. There's a -1 to the I, which is quite important. Otherwise, you would never, ever get these minus signs that I told you you should get. OK, great. Did some of you know that I had missed that minus sign? Then you should have spoken. In the future, communication, so that those who are genuinely confused actually are helped. OK. This is going to be sigma evaluated on x0, ... And then in the ith spot, I'm going to put a 0. So if I put a 0 in the ith spot, it means that I write it up until xi minus 1, and then I put a 0, and then xi appears in the I plus first spot up to xn. So this
So it's the xi plus 1.
After the 0.
This is the ith spot, and I put the value 0 in the ith spot. This is the I plus first spot, and I put xi because I want to use all those numbers. Now here I have one extra spot to fill. Yes?
Should it be indexed up to n minus 1 then on the left?
Let's see.
No, because it does and lifting R plus 1 bunch.
But in the input, I think, yeah.
Yes. Thank you. So this thing here, sigma restricted to 0, remove I n, is a map from delta n minus 1 to x. That's defined as a subset of Rn, except that I number my coordinates in Rn from 0 to n minus 1, which produces a 0 to n minus 1 here. OK, what's going on? It's actually not so hard. What's happening is the following. Suppose I have a space. Here's my space. And suppose I have a map from a two-dimensional, from the standard 2 simplex into my space. Here's my map. Tack, tack, tack. So this is I just draw the image of the map, but imagine that I gave you the actual data of the map. I need to give you a bit more data than just that, because it's going to be important to know where the 0th, first, and second vertices of this triangle go. And the way I encode it is by putting arrows on the sides of that triangle. And the way this encoding works is that I'm always putting arrows from the smaller to the bigger. This is just one way of telling you that this is the 0th vertex, this is the first vertex, this is the second vertex. Well, that, if I take the boundary of that, what I get is I get a thing which is a sum of 3 guys. The first one with a plus sign, the second one with a minus sign, the third one with a plus sign. And if this was what the triangle looked like, so I first restrict to everything where I omit 0. So that's the 0th variable. So I take this one to this one with a plus. And then I omit 1. So that's 1. I get this one with a minus. And then the last one is this one with a plus. So let's check that what I wrote there makes sense. So this is a sum of 3 one-simplices. OK, let's redo the example in the case of one-simplices. Example. If my space has a 1-simplex in it, and then I take the boundary of that, what I'm left with is, so this is where my 1-simplex landed. I get the opposite of the 0th vertex with a plus sign. So that's this one with a plus sign, and the opposite of the 1 vertex with a minus sign, and I get this. So this little simplex produces a plus and a minus, and this one produces a plus and a minus, and there's some cancellation here, and then here I get a plus and a minus, and there's a cancellation there, and so I get just a plus and a minus here and nothing else. OK, so if you want to represent something like that more formally, I think you sort of get the idea. You need to subdivide it into a certain number of little arcs, and that number could be 1 if you wanted. Then you have a single loop, or maybe 2. You have 2 arcs, and then you take their sum, and that's it. There's something else you can do, which you might think a priori that there is not much advantage. So here's an example of a 1 cycle. So suppose my space is a torus, and I'm interested in something that geometrically just looks like a circle that goes around it. And I decide to subdivide it in 3. OK, so here are 3 pieces. That's 1 piece, goes from here to here. That's 1 piece, goes from here to here. And that's 1 piece that goes from here to here. And I'm going to orient them in this way, and that way, and that way. Is that a cycle? No, it's not, because here I get a coefficient of 2, and here I get a coefficient of -2 if you compute the boundary. But I can fix that. I can say, oh, I'm taking this one with coefficient +1, this one with coefficient +1, and this one with coefficient -1. And if you just see what happens, this little path contributes a boundary of 1, and this little path contributes a boundary of 1 times -1. Add the things together, you get 0. So here you get a contribution of -1 and a contribution of 1 that cancels, and here you get 2 contributions of -1, but one of them gets multiplied by -1. Again, it cancels. So what this means is that if you choose the wrong orientation, you can make up for that by putting minus signs appropriately. And this is sort of a bit what's happening here. If you look at this triangle, if I just, what I want the boundary to be, I want the boundary to be the thing that goes around the triangle and is just oriented in a nice clockwise way without this arrow here that's going in the wrong direction. And so sadly, it goes in the wrong direction, so we can fix it by putting a minus. Now you might say, well, why did we put a minus? We may as well have put it to go in the right direction, and then we wouldn't have minuses around. Well, if you try to make this whole theory without any minuses around, then you have no chance whatsoever of creating things that are cycles, because cycles depend fundamentally on cancelling boundaries. So you need these minus signs. And that formula up there with like -1 to the I is a pretty good formula. And it will produce some minus signs in the case of the triangle, so you just live with them. Let's do an example of a 2-cycle. So again, I'm going to take my torus, and I'm going to triangulate it. OK? Ready? So I'm going to take this like that, and this like that. And then I'm going to also put another guy here. And then I'm also going to put a guy in the back, which goes here. And then I'm going to put some diagonal ones that go like that, and like that, and like that. And was it a good idea to draw it on a torus? No. So let's start all over on this picture of a torus, where we identify this side with that side and that side with that side. And so the thing that I had in mind is the following triangulation, where I have this and I could have done it with fewer triangles, but OK, that's a thing you can do. It has 8 triangles. So the first thing that you want to do is when you choose how to map delta 2 to the torus, you need to make sure that the directions of the edges are consistent. Because these things here, they're not just little pictures drawn in X. It's not just the image of sigma that matters. It's the actual map that matters. So when I want the contribution from this triangle and the contribution from that triangle to cancel, if one of them produces the map that goes this way and the other one produces the map that goes that way, those are just different elements of that set, and they will not cancel. So they need to. So OK, so by drawing arrows that go always left to right and bottom to top, that's a way of doing it that makes this work. And so this picture encodes 8 different little maps from a triangle, from the standard 2-simplex into this torus. And now I just need to decide what are the signs that I'm going to put on this. And so here's the rule. Whenever you see a little triangle that's drawn, it has, think of these edges as each one carrying a vote. And one is voting, I want to go clockwise, and the other one is voting, I want to go counterclockwise. And these two are voting for clockwise, and that one loses because it's only 1 against 2. And so you can say this is the orientation of the 2-simplex. And so this one has implicitly this orientation, that one has that orientation, and this, and that, and this, and that, and this, and that.
And the last two are wrong. I flipped it wrong.
Sorry?
The last two are flipped wrong.
Yes. Thank you. Excellent. In those types of pictures, it's very important to actually denote the orientation. And here I did it, and that's fine. And here I did it, and that's fine. And here I did it for the green, but not for the red. The red, this is the way to do it when you want to do it informally. When you don't want to triangulate things, you still need to orient things. And that tells you the orientation of the boundary. So when you're trying to build something, you should have in mind what it is that you're trying to build. And what we're trying to build is a thing with a given orientation. So suppose that the orientation that we're trying to construct is the one that goes this way. Then that's going to tell us when to put plus signs and when to put minus signs. Just like here, what we're trying to construct is a thing that goes this way. And we'll put a minus sign because that one is wrong. Here, we're trying to construct this one. So all the ones that go in the right get a plus 1. So that's a plus, that's a plus, that's a plus, that's a plus. And that's a minus, that's a minus, that's a minus, that's a minus. And so that is an example of a two-cycle. It's this simplex plus that, plus that, plus that, minus that, minus that, minus that, minus that. Yeah, here's a piece of terminology that a singular simplex is a continuous map from a standard simplex into X. So for example, when I say I want to define the boundary operator on this group of n chains, it's enough to do it on individual singular simplices. That's sort of the boundary of this singular simplex is that linear combination up there of singular simplices with coefficients plus 1 and minus 1. So let's check that here we get indeed something which is in the kernel. Well, this triangle contributes a coefficient of plus 1 for here, plus 1 there, and a minus on the diagonal. And that triangle here contributes a minus 1, a minus 1, and a plus 1 there because of the minus. And then you have cancellation here. And then this and that, you have cancellation there, and so on. One cycles have the property that you can always realize them with things where you only use positive coefficients, if you want. If you had used, like, if I don't like this, I can change the direction and have it go this way. And then I use only positive coefficients. That's an accident of one cycles. For two cycles, it is not possible to realize this using only positive coefficients. And the reason is the following. Suppose I had all positive coefficients. Well, each singular simplex contributes in its boundary 2 pluses and 1 minus. How can that possibly cancel out? Cannot. More pluses than minuses. So indeed what you learn is that a two-cycle necessarily has an even number of triangles, and with the same I guess you could have, well, the total number of triangles counted with multiplicity has to be equal to 0. OK, so I'll leave it like that. The next thing that we're going to see is that this is indeed a subgroup of that, and therefore this makes sense. So far, this is not something that has been justified. It is not true that, in general, when you write stuff like that, and you define things by saying, this is the boundary, this is like the image, this is the kernel, it's not always the case that this happens. But in our case, it does happen, and that's what we're going to see next time.